it's a joint work with my former colleague at EPFL, so Elena, Nicolas, and Laurent. So what's we were investigating is so on the left, on this slide on the left, you see the input of a neural network that is a time series. So actually, it's an audio file, and the task is to classify these audio files. So that could be like audio MNIST, where you have instead of MNIST the numbers, here you have people pronouncing the numbers, and you have to classify the numbers or according to the audio file. So we have this input, and then in the middle we have this neural network that we train. It could be any standard neural network, except that for the first layer of this neural network, the yellow box here, you have a convolution. The first layer is a convolution layer where the filter have a specific constraint. So instead of having a vector of n value, n weights that you train when you make the convolution over the time series, here you force these values to have, or this kernel to have the shape of a function, of an oscillatory function. So you see this colored waveform that symbolize a different kernel that has been learned. And what you learn is the frequency, a few parameters that are namely the frequency and the width of this function in time. And then you just keep the rest of the network as a standard convolutional neural network. So these ideas, we didn't invent that. It was started a few years before by this paper that I show you in a particular case of audio signal processing. Okay, but all this paper, they mainly focus on the accuracy of the learned details. So showing that this new layer with a constraint of having a special function to learn, it's better than like a free, flexible convolutional layer. And here in our work, we focus more on the properties of this LF. This is stands for learnable filters. So we want to understand what kind of frequency it learns, what kind of shape it has. So it's more like a orientation of explainable AI. What does it learn? So a few examples of functions that we want to learn. Example one, you see it's a Gabor function. So it's just an oscillating function with the cosine, with f is a frequency. X is a variable, okay, and you have a Gaussian windows, okay, with this exponential. That the width of the windows can be learned when you learn this sigma parameter. So you have two parameters for this function to learn. Instead of n, the size of the kernel, and of course the kernel has a size n. This is a function that is continuous and goes from minus infinity to plus infinity. So we truncate it to have just n values in center in the kernel window. Okay, and a second example. This is the second formula. It's a wavelet. So if you are not familiar with wavelets, this is a Mexican at wavelet, and you see well, it's the second derivative of the Gaussian here. The funny thing is that the shape of this wavelet is like a Mexican hat, so a very peaky in the middle, and then a small wave that vanish. And for this one, S is the parameter you want to learn, and S is the scale. So when you change S, it shrinks the wavelet or expands it. So okay, so this actually is a single parameter learning. And why? So what is the motivation of doing that? So first is to make more efficient learning process. So we will inject expert knowledge. Experts so knowledge from decades of audio signal processing, where people have investigated how the ear process the sounds and what are the small waveforms that are efficient to capture audio patterns. And these waveforms, some of them, they are called gamma tones. I will talk about that later. Then if you just learn for each kernel only 1 or 2 parameters instead of n, then you can reduce the size of your neural network and the learning time. So this is important for efficiency. And then also you have this idea of filter. You know them. They are interpretable. You know this waveform. In particular in audio signal processing, you have habit to work with them, to use them to make spectrogram, for example. And so when you learn them, you understand what is the shape that is learned, what are the frequency, what does it mean, and you can maybe better understand how the auditory system works. So just before I go to the result of this, you have a few additional hyperparameters that you can tune and we take into account. For example, the convolution stride. So when you make the convolution on the time series, you shift the window each time, and then this can have an impact if you shift too much or not enough. And after these layers, of course, you have a nonlinearity. So we choose a ReLU, a standard one, but you could also test other things. Okay. So first, the result of on accuracy. So there's just one slide to say that this approach is let's say as good as a standard CNN. What could do a standard CNN? So if you look at this table, you have like the first line is a complex big model for audio with a lot of trainable parameters, and just below that you have this LF, so a learnable filter version of it, where we change only the first layer with our learnable filters. That reduce the number of trainable parameters a lot, and then we get a better accuracy. When we I have to say a few words about the data set. So it's audio MNIST again. So people are just some person are reading, saying the numbers out loud, and then you have to guess which number it is from the audio file. Okay, the other models at the bottom, they are custom. More, let's say, optimized, smaller neural network, where you have this learnable filter and you have different function that you can put on the kernel. So one is gamma tone, another one is signet, which is like a sine, cardinal sinus, which is another paper that proposed this. We wanted to compare it, and the last one is wavelet. So what you see, of course, our method is the best, but this is by like really a few percent or even 1%. So it doesn't mean much. And what I want to just you to focus is that it's not like why it's better than the state of the art. It's more or less the same. And what we want to do is that we want to show that is not worse. Even if we reduce the number of parameters and the flexibility of this first layer, then the performance is more or less the same. Okay, very high. Except for the last one, you see the wavelets, because you drop by 10%. And this really shows you that wavelets, they are not very well adapted to find oscillatory pattern, of course. So audio patterns, they are more adapted to analyze images or decompose images. So in this case, it doesn't work well. And so that shows that the function we use also are known by audio experts to be the one that are the most efficient. Okay, and this is what we see on the result. So now, what can we learn from this learning of the function? First thing, so here you have on the top the equation for the gammaton function, which is some sort of optimal waveform that is used in the human hearing, model the human hearing. So you have capital A is a constant normalization constant that depend on just on two parameters. That so gamma is something fixed. It's the order of the gammaton is fixed. B, this will be learned, and it's related to the bandwidth. So it will be also related to, in time, the width of the gammaton. And maybe you can see on the right, like the result of the gammatons that we get. So each waveform of different color is a gammaton, and you have different frequencies. The highest frequency is at the top, and then at the bottom you have the low frequency. So if you look at the formula again, you have x to the power some order, and that gives you an increase when you start from 0. Then you have this exponential that at some point just will create a decay of the function. And you have this cosine part, which makes the oscillation. And you learn B and F. So you see that from this gammaton, you have a relationship between frequency and this shape, of course, because when you have like a slowly oscillating wave, you need a large window to get all the intuitivity of the wave. So you need to have a larger window. So that's what we see on these plots. And if we look at the plot on the left, the frequency versus bandwidth. So you have let's say two solid lines. So the blue and the orange. They are lines that model that experts in audio processing have just come out with to model the human hearing system and the way it processes the audio, the hearing. So you have this blue, it's called the Park scale, and orange is the ERB, equal rectangular bandwidth. So they are a bit different. So there are two approximations. But then they are quite similar when you have low frequency. So then the points of different color are each point correspond to a filter that has been learned. And for different, the color represents the order of the gammaton. And if you look at the literature in audio signal processing, the gammaton that are closer to the human hearing model, the model that are closer are of order 4, maybe maybe 2, but more of order 4. That are the red dots here, and they follow more or less the Park scale. So two important remarks here. If you change the order, then you can still learn, of course, to classify the data, and you get more or less the same accuracy. But the learning gives you different relationship between frequency and bandwidth. You see, for example, the Gabor, which is completely different to the other. So we fix the gamma, the order, and the thing you have to understand is that the hearing process, of course, you have some, so it's a part which is in the brain, but you have also a part which is in the ear that are also additional constraints, and that probably force the ear to have some gammaton close to order 4, let's say. But then if you had some other freedom, then it could also be efficient, and it could learn another distribution. So, and second point, when you look at high frequency, then it doesn't match or as closely as it is for low frequency, these filters. And this is probably because in the dataset we have also, we have more information in the low frequency. So it's easier to learn, and then in the high frequency, maybe it's not, the learning is not reached the optimal state. And so that's probably limited because of our data. Next property, and I will finish with that probably. So on the axis, you have the number of filters. So we trained for this example 32 filters, and then you have the frequency, the center frequency learned for these filters on the vertical axis. And you start with the gray. So initial is like a linearly spaced filter, and then you go, you learn, and you realize that the distribution of frequency change with learning. And at the end, if you look at the filter from 0 to 15, then they have some value that are below the initial point. And that means that you have more filters that focus on the low frequency band. So you, of course, it's expected, because you need more filter for the low frequency, and maybe more information is there too. But it's expected, but we would expect a more pronounced line like this. So this is something also that has to be investigated further. We would like to know if it's because of our dataset. Maybe we have, if we have different dataset, it could be different. If we have noise or something else, then could also influence this distribution. So just to conclude with that, so this approach for learnable filter gave you some maybe more efficient neural network, because you have less parameter to train. It's more interpretable, and but then also with the interpretability, it opens the door to other new insight for the audio part, the audio expert and the expert in auditory system. And you have still many questions, so we would like to answer or to address. For example, the rest of the CNN is completely free. So maybe the first learning is not so important, and the network, the first layer, let's say, is not so important. And if whatever you get, then the rest of the network will adapt. Or this is something that we have to check. What about other tasks, also audio tasks, to apply to it to? What is the robustness to noise of this? And also something would be interesting is that you extend it to a 2D or 3D even, because in 3D, it's very difficult to do deep learning with the convolution size, which is much bigger. So this kind of constraint filter could be a solution. So, okay, thank you very much. That's all I wanted to say.